So hello everyone, I'm David from UCST. Today I'll present the 2026 contest on post-placement buffering and sizing. This contest was, as mentioned, jointly organized by UCST, POSTECH, and Fudan University. Here's the outline of today's presentation. I'll start by introducing the contest and its motivation, followed by the problem formulation. I'll then walk through the benchmarks and contest evaluation flow. Then I'll present the evaluation methodology and results. Finally, I'll close with acknowledgements and the roadmap for next year. This slide explains the motivation for this contest. In today's advanced technology nodes, post-placement time enclosure is becoming more and more difficult. Two key techniques for addressing this challenge are repeater insertion and gate sizing. Based on this, the goal of the contest is to develop a post-detailed placement buffering and sizing tool. This tool should improve power, performance, and area while also fixing ERC violations. Importantly, the contest is designed to reflect real industry conditions. Our benchmarks include practical physical constraints, such as fixed macros and IOs, the power delivery network, soft placement blockages, and fixed routing resources. Together, these constraints reduce available white space, increase congestion, and make legal and effective post-placement optimization much more challenging. During the preparation stage, we had many discussions with experts in the field and received a lot of helpful feedback. Their input helped us shape several key design choices for the contest. This slide highlights some of those discussions and decisions. For buffering, we allow inserting both buffers and inverters since both are commonly used in practice and expand the optimization space. We introduce a displacement penalty. This is to discourage contestants from improving PPA simply by moving cells excessively. That's not the main focus of this contest. In total, we provide 12 test cases with design sizes ranging from about 15,000 to 1.4 million instances, and with up to 220 macros. For computing resources, we aim to make the evaluation process transparent and accessible to all contestants. In particular, we thank NSF Chips Hub and Purdue University for providing access to the Anvil supercomputer. We also developed an equivalence checking tool to ensure the logical equivalence of submissions. We sincerely thank everyone who contributed suggestions during the proposal and contest design stages. There have been several closely related contests in the past, however, many of them simplified important aspects of real-world physical design flows. For example, the ISPD 2012 and 2013 contests focused only on gate sizing. They operated purely at the logic level, without considering placement and other physical design constraints. Similarly, the ICCAD 2024 contest also focused only on gate sizing. It did not allow buffer insertion, netlist edits, or cell relocation. The ICCAD 2025 contest had a setting similar to our ISPD 2026 contest. However, its test cases were simplified and mainly focused on post-placement PPA metrics without considering routing quality. The MLCAD 2025 contest encouraged AI-driven logic resynthesis for timing optimization, but the problem formulation remained relatively abstract and did not include physical blockages or routing considerations. Here's a table from our invited paper that summarizes the key differences between these contests. Next is the contest's problem formulation. Given the gate-level netlist, legalized placement, standard cell library, and various design constraints, the goal is to find buffering and gate sizing solutions that improve timing and power while also fixing ERC violations. We evaluate the solution quality using a weighted combination of several metrics, including TNS, power, ERC violations, runtime, cell displacement, and global routing overflow. The solution must maintain placement legality, preserve logical equivalence, and ensure that fixed elements remain unmoved. Next, I'll present the benchmarks and evaluation flow. We use 4 base designs: AES, JPEG, Ariane, and BSG chip, synthesized using both commercial tools and IOSIS. Commercial netlists are anonymized. Each design has 2 variants differing in TCP and utilization, spanning an easy to hard difficulty range. All benchmarks use the ASAP7 7nm predictive PDK with 3 threshold voltage variants, RVT, LVT, and SLVT, each containing approximately 90 logical cell types with multiple drive strengths, enabling contestants to explore timing power trade-offs. As shown on the right, benchmark generation follows a fixed RFS-based pipeline. This is synthesis, floor planning, macro placement, tap cell and PDN insertion with soft blockages, and global and detailed placement. Human macro placement solutions come from the TLOS macro placement repository. Finally, all buffers are removed, and the debuffered def and Verilog netlist are written out as contest inputs. The benchmark suite spans 15K to 1.4 million instances across 8 public and 4 hidden benchmarks. Standard cell count includes physical cells, so in some cases, net count is less than standard cell count. The 4 hidden benchmarks, 2 Ariane and 2 BSG chip variants, are the most challenging test cases and are not revealed to contestants. Here are the public benchmarks. Each design has 2 variants. The base variant uses commercial synthesis with manual macro placement. The V2 variant uses Yosis synthesis with open road macro placement and includes soft blockages, further constraining available whitespace for buffer insertion. Images show the V2 placement layouts. Now we present the 4 hidden benchmarks, variants of the public Ariane and BSG chip designs, ensuring no unfamiliar design structures for contestants' tools. Soft guides are added around macros. For BSG chip, one variant uses human macro placement and the other higher RTL MP. Both Ariane variants use human placement. Now we'll look at contest evaluation details. The figure on the right shows our evaluation flow. Contestants receive 4 input files, a post-detailed placement def with fixed macros, IOs, PDN, and soft blockages, a debuffered Verilog netlist, an SDC file specifying clock period and IO delays, and ASAP7 LEF and multi-VT library files. The output must include a modified Verilog netlist and a legalized def. Evaluation runs entirely within the OpenRoad infrastructure, including GR-based parasitic extraction, then timing and power analysis. A custom equivalence check verifies 4 properties: functional equivalence of resized cells, buffer and inverter only insertions, preserved pin-to-pin connectivity, and buffer tree parity, meaning that each source sysync path must contain an even number of inverters to preserve signal polarity. For evaluation, we provided a container to both organizers and contestants, so contestants could evaluate their solutions on local machines before gaining access to the contest resources provided by Purdue's ChipSub. Contestants upload a zip file with a setup script to install and build packages into the fixed container environment, plus a run script that we execute for each benchmark test case. For each submission cycle, we create a fresh resource-limited Apptainer instance on Anvil for each team. Ultimately, we saw some resource and access bottlenecks that we will need to solve. Our scoring function is a weighted sum of relative improvements over the pre-optimization post-placement baseline. We apply several penalties for excess runtime for both the submitted tool and the evaluator, displacement of movable cells, electrical rules violations, and global routing overflow as computed by OpenRoad's GRT, summed over all layers and all G cells. Finally, violating any of the constraints listed here in the red text results in 0 score. For example, nothing in the floor plan, including PDN and the placement of IOs and physical cells, can be changed. The team's score is given by a weighted sum over all. Next come the results. We opened registration in October and published our initial evaluation toolkit. 36 teams registered. The full set of benchmarks was released in December, and 17 teams made alpha submissions by January 12th. Beta submissions were due on February 2nd, and 13 teams made final submissions. but one of the teams withdrew afterwards. Throughout, the feedback to teams included scores and anonymized rankings. We'll announce the results right now. I will now show you the top 3 anonymized final scores. The Open Road Resizer achieved our baseline score of 1,107. Third place achieved a score of 1,315, a 19% improvement over baseline. Second place achieved a score of 1,347, a 22% improvement. And finally, first place achieved a score of 1,438, a full 30% improvement over the baseline. We can see that of 13 submissions, 7 were able to outperform the baseline, varying from an 8% improvement to the winning 30%. Now, we will take a look at contestant performance over individual designs. We can see here that the first place team was able to score the highest on most designs. However, the sixth place team was able to take the lead on 3 of the 4 hidden designs, which is quite noteworthy. Looking at this chart here, we can see that the contestants were able to push quality of results much further on the smaller designs, AES and JPEG. We can see here that the first place team is dominant in TNS. We can also see, however, that TNS improvement does not account for the whole picture of scoring and of the first place team's success. For example, they achieved an 87% reduction in Ariane V2's TNS, but their final score improvement only totaled 18%. In the leakage power ranking, the first place contestant again does best. The 2 hidden BSG chip designs could not be optimized for leakage by any contestant, nor the Open Road Resizer. These results highlight the multi-objective nature of buffering and sizing, as we witness teams focus on different quality metrics. Finally, we consider dynamic power. Recall that these 3 factors, TNS, leakage power, and dynamic power, were the primary considerations in our scoring, but there were others, such as displacement or load violations. Before I announce the winners, I would like to acknowledge those who made this contest possible and discuss our roadmap for next year. Building on this year's contest, we plan to place greater emphasis next year on the robustness and scalability of buffering and sizing strategies. We also hope to introduce more challenging and realistic conditions. For example, we are considering directions such as multi-corner, multi-mode timing constraints, incremental infrastructure improvements, post-CTS sizing and buffering, hold timing constraints, iterative ECO style optimization, and multi-stage evaluation. Other learnings from this year's contest include the need for more rigorous evaluation and policies to reinforce the spirit of the competition. These ideas are still under discussion, and we very much welcome suggestions from the community on problem formulations, evaluation metrics, and possible new challenges. It is now my pleasure to announce the winning teams of the ISPD 26 contest. After a brief honorable mention, I will announce the top 3 teams, after which I will play videos that they have sent in. We would like to extend an honorable mention to PKU from Peking University. Though they ranked in 6th place, their solution was able to achieve impressive results on the hidden test cases. In 3rd place, congratulations to HLFC from National Tsinghua University. The team have sent in a video. I would like to play it for you now.
Hello everyone, we are Team 29 HLFC from National Tsinghua University in Taiwan. Our team members are Zhe Jianling, Zijiang Hong, Fenghua Fu, and Pei Qiu, and our advisor is Professor Junyao Wang. The person in the center is our advisor, Junyao Wang, and from left to right, the team members are Zijiang Hong, Pei Qiu, Zhe Jianling, and Fenghua Fu. This figure shows our workflow. First, we generate 2 types of netlist with different threshold voltage, RVT type netlist and LVT type netlist. Next, we use Open Road to optimize both netlists. We begin by downsizing non-critical gates. Then we iteratively perform repair design and repair timing to further improve the results. Finally, we select the better result as our final output. Thank you for your attention.
Thanks. In second place, congratulations to PTSD from National Tsinghua University. This team have also sent in a video, and I'd like to play it for you now.
Hello everyone, we are Team 31 participating in the ISPT 2026 contest. Our team members are Tingjun Chen, Minqi Xu, Haoyu Cai, Chunwen Pai, Zhouyi Huang, Chunyao Wang, and Yongchi Chen. In this presentation, we will introduce our approach to improve circuit performance.
And our approach explores multiple optimization flows to improve circuit performance. First, we read the design file and create 4 optimization flows with different voltage type preprocessing strategies. First is no preprocessing. And second, we change the gate voltage type to R. And third, we change the gate voltage type to L. And fourth, we change the gate voltage type to SL. And each circuit is then optimized using a modified open row gate sizing and buffering framework. The main modification is to allow the gate sizing process to explore more possibilities during optimization. Finally, we compare the results and select the highest scoring design as the final output. This multi-flow strategy allows us to explore different design possibilities and choose the most effective optimization outcome. And thank you for listening.
Thanks. And in first place, congratulations to Team Iris Lab as the first place winners of the ISPD 2026 Buffering and Sizing Contest. Their submission was a collaboration between National Taiwan University and the National Taiwan University of Science and Technology. Congratulations. The team have also prepared a video for us.
Hello everyone, we are Team 33, Iris Lab, representing National Taiwan University and National Taiwan University of Science and Technology. It's our honor to present our solution for the ISPD 2026 contest regarding post-placement buffering and sizing. Our team is composed of students from NTU and NTU ST. Yu Xianghuang, a second-year master's student from NTU GIEE. Guanyu Fanjiang and You Jiaguo, both senior undergraduate students from NTU EE. Yunhan Liang, a senior undergraduate student from NTU STEE. This work is conducted under the guidance of our advisor, Professor Iris Huiru Jiang. Our proposed flow is built upon 3 tightly coupled pillars: static timing analysis, physical optimization, and legalization. Unlike conventional sequential flows, our work ensures that gate sizing and buffer insertion are driven by high-fidelity timing feedback. This circular dependency allows us to explore a vast solution space for optimal outcomes. To achieve this, we have implemented 4 key technical features. First, we focus on accurate performance modeling. By establishing a reliable timing power analysis, we ensure that every optimization step is grounded in precise timing and power measurements. Second, our flow performs simultaneous optimization. Instead of treating sizing and buffering in isolations, we address them concurrently within a unified flow to better manage the trade-off. Third, we use the open road infrastructure specifically for placement legalizations. This ensures that during our optimizations, all cell instances are realigned to legal sites without any overlaps. Finally, the entire system is powered by a GPU-accelerated workflow, providing a high throughput needed to scale with large test cases. In conclusion, Our flow integrates multiple optimization stages into a single unified framework, supported by reliable performance analysis. This concludes our presentation. Thank you for listening.
Thanks. Thank you for joining us for this presentation, and thank you to all of our contestants for making this a great ISPD contest. Congratulations once again to Team Iris Lab for their success. You can find detailed results and additional materials on our contest GitHub, which you can find on the ISPD 2026 website or by following this QR code.